Hey everyone, welcome back, and let's write some more neat code today. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a very popular problem and probably one of my favorite problems of all time. It's jump game. So this is a very popular dynamic programming problem, but it can also be solved in a greedy way. I'm going to show you both solutions and then we're going to code up the greedy solution, and it's very little code, so that's the good thing, but it's a pretty clever problem, so let's dive into it. So we're given an array of non-negative numbers, so all of them are going to be 0 or positive, and we're initially positioned at the first index of the array. So for example, in this input array, we're positioned at the first index, or the 0th index, right? The first position. So this is where we're going to start. We're going to start in this position. And so for every value in the array, for every element, the number itself, for example, number 2 in the first position, represents the max jump length that we can perform at every single position. Basically, what that means is from this first position, we can only do a max jump of 2, meaning our max jump can only get us to this position, right? And another example, from here, since this is a 1 value, the max jump we can do is a 1 jump, meaning we can only jump to the next position, right? Obviously this is a 3, the max jump we can do is a 3, meaning we can reach the end position, the 4, from here, right? Because we can do a jump of length 3. Given all of that, given that we're positioned here and that every value represents the jump size, we are only asked, can we reach the last index? So starting from here, given these jump values, are we able to reach the destination, which is the last value in the array? So in this first example, the answer is yes, so we return true because yes, we can reach this position. How can we do it? Well, we start here, so we can do a jump of length 2, or we can do a jump of length 1, right? We don't have to do the max jump length. We can choose to do 1 jump. So then let's say we're at the second position now, right? So now we're at 3. We can either do a jump of length 1, a jump of length 2, or a jump of length 3. And we're going to do the 3, right? Because now we're here, meaning we're at the last position, right? We're at the last position, therefore we did reach the end, therefore we can reach the end, so we return true. Okay, so let's look at a different example. Let's look at this example. Can we reach the last position or not, right? That's the question we are trying to answer. Let's brute force this. How can you brute force this problem? Well, let's look at every possible path we could take. So remember, we start over here. What's every single path we could take that could potentially get us to the end? If we find even a single path that can get us to our destination, then we return true. So for each of these values, I'm going to give them an index. So we know that 3 is at index 0. This is index 1, 2, 3, and 4. So these are the indices. So I'm going to start at position 0, right? We're starting at position 0, and see the value we have. The value we have is 3. That means we can make a jump of length 1, a jump of length 2, or a jump of length 3. If we make a jump of length 1, you can see we get to a 2, right? So the next position, if we took a jump of length 1, right? So from here we jump 1, then we're going to get to index 1, right? So that's what I'm going to put here. We're at index 1. If we take a jump of 2, we're obviously going to get to index 2. If we take a jump of length 3, we're obviously going to get to index 3. So these are the indices, right? So that's what each of these is representing. Each of these values is representing the index. The value on the edge here, 3, 2, 1, these are representing the jumps that we're having to take, right? We're going through all this work because we're showing the brute force solution. So from here, we're at index 1, right? we're at index 1, we have a value 2. That means we can do 2 jumps, right? A jump of 1, which would get us to index 2. So one decision is a jump of length 1, which gets us to index 2, or we can take a jump of length 2, right? Because this is a 2, so then we get to index 3, value 0. So we can take a jump of length 2 and then get to index 3. So now I'm just going to quickly start filling this tree in, and you can see that we're going to be doing a lot of repeated work, and that's what we're going to do. So this brute force solution, I think it's roughly n to the power of n, right? Where n is actually the length of our input array, right? N is the length of our input array. So this is roughly the big O time complexity of the brute force solution. I'm going to show you how to cache this, and when you cache it, you can actually make this a big O of n squared solution, but we need a little extra memory for that. But basically, we're going to optimize this brute force solution. After that, I'm going to show you the greedy solution, which is actually big O of n time complexity, and you can skip to that if you'd rather just do that. So from index 2, we see we have a value 1, right? That means we can only make one jump, and that jump is length 1. And when we do that, we jump from here to here, we get to index 3. Funny enough, that's where this path is also. So we're at index 3. That value is a 0 though. So what does 0 tell us? 0 tells us we can't make any jumps, right? We're making jumps of length 0, which means we're not really jumping anywhere. So basically a 3 is a dead end for us. So basically this is a dead end. So we can jump of 1, right? And when we here, this was a trap, right? We index actually immediately stop this, say false, right? That tells us we've already visited that, we've already gone down that decision before, and it's false because we could not reach the end. So now when we're over here in this position, index 2, we don't have to do anything, right? We don't have to continue that decision of making a jump of 1 and then getting to 3. We can actually immediately stop this, say, okay, no, we know that from here we cannot reach the end. And you know what you might have noticed by now is none of these paths can reach the end, right? So if we were doing the DP solution or a cache solution, we'd say, okay, DP of 3 is also false, of 1 is false, right? Because take a look at this 1. When you take 1, or rather this one, right? This tells us we're at index 1. Both of the paths lead to 2 and 3, and those are also false. So DP of 1 is also going to be false. And when you look at the root of this, the root tells us when we started at the first position, right? That turned out to lead to all 4 x's, right? We basically a little bit of the brute force solution, linear time solution, a big O. This cache, you can get this solution to be O of n squared time complexity, but there's actually an even better solution. We can be greedy and we can get a linear time solution, a big O n solution. Let me show you how to quickly do that, and then the code is actually pretty short. Let's take a look. Okay, so now let's get into the actual greedy solution. So this is greedy and it's going to be linear time complexity. This problem has a pretty simple solution. We don't actually need dynamic programming. Let's look at we know that this is the starting position, right? The left or the first index is the starting position. Our goal is to get to the end position, right? But let's actually look at this in reverse order. Let's start at the end position and then see if we can work our way to the beginning in a sense, right? So in actuality, the first index is the starting position. This is the goalpost, right? This is the position that we're trying to reach. But we can see, let's work our way backwards. Let's take a look at this position. It's right next to the goal, right? This is our goal, and we're just pretend like this is a goal. So this is our goal, and this is right next to the goal. The 1 means that we can make a jump of length 1. So really, we go here, we make the jump, and now we're at the goal. What does that tell us? Doesn't that tell us that we don't actually need to reach this position anymore, right? If I'm starting over here, right? Let's say we're starting over here, this guy over here can literally reach the end position, right? We know for a fact this guy can reach the end position which we're trying to reach. Doesn't that mean that we can take our goalpost and then shift it over here, right? Because we're not trying to get here anymore. Now our new goal is to get to this position because this can reach the end position, right? So from here, we're now trying to get to this position. We move the goalpost a little bit closer to us. So now we're going to put that goalpost over here. So now let's look at the next position in reverse order. So this is also a 1. That's good for us because we can make a jump of length 1 over here, right? Now, notice this guy can't reach the end position, right? Which is bad, but it can reach this position, which is where our goalpost is, which is all that really matters, right? As long as we can reach the goalpost, we can keep shifting it. So now let's shift the goalpost one more time. We can move it just a little bit closer to our initial position. Now we work our way backwards again. We're at a 3. That tells us we can make a jump of length 3 or less. So it could jump 1, 2, 3 all the way over here, right? That 3 could jump all the way to the end, which is awesome for us, but that's actually unnecessary because we see the goalpost is even closer than we expected. Now it's over here. So it can make a jump of 3 or it can make a jump of length 1. It makes no difference because either way, we can now take that goalpost and keep shifting it. So now the goalpost is over here. We're almost done with this problem. Now we see we're at 2. We can make a jump of length 2 or 1, and then we reach here, right? We reach the goalpost from the first position, right? Therefore, we're moving it one last time to the start position. What that tells us is, yes, we can return true because from the starting position all the way at the left, we are able to reach that end position, right? We're able to reach the last position, so we return true. And we did this in linear time because we're greedy. We kept shifting that goalpost as close as we could to us, and we don't even need extra memory for this. So that's the greedy solution. And we don't have to have a big old decision tree. We don't even need a cache or anything like that. We're literally just doing this greedy linear time with a loop. Now let me show you how to code it up. It's pretty simple. So the only main variable we really need is a goalpost, right? So initially we are going to have that goalpost or goal or whatever you want to call it at the end. So it's going to be the end, right? We're trying to reach the last index in our input array. And remember, we're going to be working our way backwards in the input array. So in Python, this is how you do it. You just take the length of the input and you can do a range loop with it. So basically what we're doing with this one line is we're starting at the last index and working our way to the beginning up until we reach the initial index, the first index. So now I want to know if we're at position I, right? I plus nums of I, right? Nums of I is going to be the jump length, right? I want to know, can this jump starting at position I, taking that maximum jump, is it greater than or equal to the goal? Because if it is, that means we can reach the goal. What do we do when we can reach the goal? We shift that goalpost even closer to us. So if we're able to reach the goal from here, we can update the goal to be I. Right? I is the position that we're jumping from right now. So that's where we're going to shift the goalpost to. Awesome, right? That's literally all you have to do. Now, when we reach the end, right, either two things will be true. Either goal will now be 0, right? Meaning that from position 0, we're able to reach the goal. Or goal will be greater than 0, which means we were not able to reach the end of the input list. So we can make a condition to return that. So return true, goal is equal to 0, else return false. So this is how you solve jump game in linear time with the greedy solution. No extra memory is required, and this is how you do it in Python. In Java or C, it might just be 1 or 2 lines of extra code, but the general solution is the same. So hopefully you are able to code it up, and I reach the end position which we're trying to reach. Doesn't that mean that we can take our goalpost and then shift it over here, right? Because we're not over here, right? The jump. And let's take a look at this position. It's right next to the goal, right? This is our goal. And we're just pretend like this is a goal. So this is our goal. And this is right next to the goal. The one means that we can make a jump of length 1. So really, we go here, we make the jump, and now we're at the goal. What does that tell us? Doesn't that tell us that we don't actually need to reach
Yes.